hosts, Your Excellency, dear colleagues. Um, Thank you very much for the invitation. Uh, Good morning, bonjour, kalimera. We will discuss together issues of urban overheating. We will discuss why our cities present a higher temperature. And is it a real problem? Yes. It is one of the more documented phenomena of climatic change. This is a phenomenon that was first registered at the beginning of the last century in London, where they have understood that, in the CBD area of the city, temperature was about 2 to 3 degrees higher than the surrounding area. Now we have documentation about the magnitude and the characteristics of the urban heat island for more than 450 large-scale cities around the world. And in this graph, you can see actually the documented, let's say, magnitude of the urban heat island in 110 different Asian and Australian cities. As you can understand from the graph, the average magnitude is of the order of magnitude of, let's say, 5 degrees, 6 degrees. And in some cases, we have much higher, let's say, temperature increase in cities. This is very important. This is very serious. But it's not just that, because actually, it's not just the increase of the temperature in our cities. This is combined with many other issues that have to do with, for example, the prolongation of the hot spells. You see, for example, in this specific graph, the hot spells above, let's say, 37 degrees and also the hot spells above 40 degrees in the Mediterranean area. And you can easily understand that there is a tremendous increase of, let's say, the periods with very high temperature or with excessive temperature in the Mediterranean. And unfortunately, it's not just that. A part of the temperature increase and the prolongation of the hot spells, we have a tremendous increase of the frequency and also the magnitude of heat waves. And you see, for example, what is happening in the Mediterranean during the very last years. It is evident that such, let's say, an increase of the temperature and prolongation of, let's say, the hot spells, we may have a serious impacts on energy, health, sustainability, survivability, quality of life. And during the very last years, there are a lot of research that has been carried out, and many studies that have documented actually what is happening regarding the energy and health and all the other impacts of climatic change in cities, which is called as local overheating. Especially as it concerns the energy consumption and the energy supply. This is extremely well documented. And of course, it is very evident that once we have higher temperatures, the energy consumption for cooling is increasing, let's say, tremendously. And we expect to have a lower demand for heating. But it's not just that. The problem is that the higher temperatures increases the peak electricity demand, obliging utilities to build additional power plants. At the same time, decreases the efficiency of the power plants, nuclear and thermal power plants, and also the performance of, let's say, the distribution systems. All these issues are very well documented. And actually, for example, we know very well that the global energy penalty per square meter of a city is close to 2.3 kilowatt hours per square meter, while if you wish really to have the global energy penalty per square meter and the degree of temperature increase, it is much, let's say, important is 0.7 kilowatt hour per square meter and degree of temperature increase. But I think that is much better if we report the penalty as a function of, let's say, per person, which is close to 230 kilowatt hours per person because of the, in average and all over the world, because of the global and the local overheating. So it is a tremendous penalty that we have to pay because of the actual, let's say, increase of the temperature in our cities. And this brings us to the major problem that we will face in the near future regarding the energy, let's say, supply and demand in our buildings. And this has to do with the future energy consumption for cooling. If you try really to plot which is the actual energy consumption for cooling, it is not so high. It is, let's say, actually this red line you see there. But once we try really to develop some scenarios about, let's say, the future energy consumption for cooling the building sector by 2050, and we may, let's say, assign 3 different scenarios, one of low development, one of average development, and one of very fast development, we may realize, for example, that under, let's say, the low development, we may have a tremendous increase of the cooling demand by 2050, which can be of the order of magnitude of 320%, 3 times more than the actual energy consumption. Once we consider an average development scenario, which is much more probable than the low development one, the expected energy consumption for cooling is much higher, and it's close to 750%. While if we consider a very fast development scenario for the world up to 2050, the expected increase of the cooling demand will be of the order of magnitude of 2,270. Once uncertainties are taken into account, numbers are much, much higher, and we may, let's say, reach an increase of the demand for cooling up to 2,600 to 700%. This means that we need to have a tremendous number of new power plants. We need to have a lot of, let's say, energy consumption, a lot of conventional or non-conventional fuels, a lot of peak electricity demand, a lot of emissions, CO2 emissions, a lot of pollution. So we need really to face the problem of overheating in our societies. I will stop really presenting you the data about energy because it's something that is very well developed, but I like to move to something which is extremely important. The impact of overheating on vulnerable population, on low-income people. You know very well that low-income people is living in, let's say, non-well-protected buildings. They don't have really the means to be protected, and at the same time, because of economic reasons, they don't have really the means to cover the energy needs. So these, let's say, vulnerable population, low-income households, let's say, are the first victim of climatic change. Do we have enough evidence about the impact of local climatic change on low-income population? Yes. Data have been collected in many, many countries all around the world. I would like to show you some recent data we collected last winter in a developing country, in the developed country in Australia, where really, usually we don't consider that there is energy poverty. In Western Sydney, really in low-income households, indoor temperature during, let's say, the summer, not during heat waves, it has exceeded 40 degrees, as you can see there. But while during the winter period, indoor temperature was 7 degrees. So local overheating has really tremendous impact on indoor comfort and also threatens the, let's say, health conditions in, let's say, low-income people. Unfortunately, it's not just the increase of the temperature, because people try really to be protected and they close windows, doors, everything. The CO2 concentration and the other pollutants indoors is increasing tremendously. And you can see that together with the 40 degrees indoors, we may have an increase of the CO2 concentration up to 4,000 ppm, which means 4 times more. So this is a serious problem, and this is a serious threat for, let's say, the health of people. And this brings us to the real problem of, let's say, urban overheating, and what really is going to be the main future and the main issue for the future about, let's say, overheating: health. The impact of overheating, the impact of local and global climatic change on health. This is not such an easy, let's say, task. It's not a, let's say, deterministic approach where you can write an equation and find the relation and the association between temperature and mortality or morbidity. Because there are so many other issues that have to do with, let's say, the issues of health, and especially demographic issues, issues that have to do with, let's say, prosperity and income, issues that have to do with, let's say, the local climate, issues that have to do with the socioeconomic aspects, and issues that have to do with the local infrastructure and health. So it is a little bit, let's say, complex to understand and analyze. But first, what is important to understand is that we don't have the same response to heat. For example, people living in the south of Europe or in the north of Australia, they may respond and they may tolerate much higher temperatures than people living in the northern countries like Finland or Sweden. This is very clear from all the studies that have been performed during the very last years that shows that the threshold temperature above which heat-related mortality is increasing is really much lower in the northern part of Europe or in the northern part of the northern hemisphere. And this is something that has to be taken into account from all those that they say that is good for the northern climates to have, let's say, the increase of the temperature. And I'd like to show you the results of a very recent study performed in Europe in different, let's say, European cities, correlating the indoor temperature, the outdoor temperature with heat-related mortality. And you see, for example, the results for some Mediterranean cities, Athens, Barcelona, Madrid, Marseille, etc. And you can see that the threshold temperature above which heat-related mortality is almost increasing exponentially is between 28 to 32 degrees. Once the same curves are plotted for, let's say, northern climates, London and Stockholm and Finland, etc., you may see that the threshold temperature is much lower, 21 to 23, 24 degrees. So this is very important once really we plan the mitigation, the adaptation, and the resilience plans, let's say, for different parts of the world. And this affects very much the quality of life in our cities, because actually we know that during, let's say, extreme events, during heat waves, a very high part of the local population is suffering and is dying. And unfortunately, up to now, we have data only from developed countries. We don't have data from developing countries because the systems collecting data, health data, are not really so well developed. What do we know? We know actually that in less, let's say, developed countries, during heat waves, almost 30% of the population is affected and may, let's say, suffer from increased mortality and morbidity. While in countries with, let's say, very advanced systems of protection, this, let's say, percentage may be reduced up to 5%, but even 5% is very high. And I'd like to show you the map of the heat-related mortality in Sydney, a very developed, let's say, city, one of the best cities in the world. In the western part of the city, which is next to the coast, temperatures are very low. In the western part of the city, which is close to the desert, we have almost 10 degrees of temperature difference in a distance of about 40 kilometers. I just like to show you the mapping of the heat-related mortality during February 2019. You see that during the same day, normalized data in the western part of Sydney, because of the overheating and because of the lower income, heat-related mortality was 3 times higher than in the eastern part of the city. So there is a tremendous impact of overheating on our quality of life and also on our health. But it's not just the outdoor climate that affects really heat-related mortality and the impact on health. While, let's say, the outdoor environment and the outdoor, let's say, temperature may increase the risk for heat-related mortality up to 6%, once people living in these cities with, let's say, high temperatures do not live in proper housing, this, let's say, risk factor, it goes up to 80 and 22%, which means that it's not just, the outdoor environment. It is the combination of the outdoor environment with the quality of our buildings. So our new future and our future research has to concentrate both on the better quality of our cities, on the better quality of our, let's say, buildings. What's about the future? Many scenarios, many papers, many works about the future mortality and the future impact of overheating in health. And everyone is expecting that this will increase. But this is not sure at all, because we are adapted from the physiological and technological way. If you try really to, let's say, analyze the data of heat-related mortality with temperature during the 100 last years, you will see that although temperatures have increased, heat-related mortality has decreased. Why? Because we are better, let's say, adapted to this, and because we are better, let's say, prepare to face the problem of overheating. So it is a very complicated and very important issue, but it is the main issue that may affect, let's say, our future. I have presented you bad news. Now it's time for good news. During the last, let's say, 20 years, there is a very intense research trying really to investigate ways and technologies to decrease the temperature of our cities. So we have developed a very high number of very advanced mitigation technologies, and you see some of them in the screen. I don't really like to go through all the mitigation scenarios. I don't have the time. But I like to start by telling you that what is important trying really to develop a mitigation plan for a city is to have a very good diagnostic tool to understand what is happening. It's like in medicine where we need really to scan someone to understand what is happening and then give the proper medicines. If we don't scan, if we don't know, if we are going, let's say, in an empirical way, we risk to solve another problem. So actually, we're able really to scan and have information with a resolution of 2 centimeters by 2 centimeters in a city. And you see, for example, some aerial pictures that we have taken for, let's say, an Australian city, Alice Springs, and shows the hotspots 2 centimeters by 2 centimeters. And this helps us really to understand how and where we have to intervene. Or let's say the use of very advanced UAV systems can really help us to understand where the problem is. What is very important as it concerns the development of mitigation technologies is the progress we have achieved in regards of, let's say, mitigation materials. Materials that can be used in the city, in buildings, to, let's say, help to decrease temperature of cities. And many years ago, we started with the so-called, let's say, cool materials, very reflective materials, white materials that really reflect radiation and decrease the temperature in cities. But it's not possible to have white everywhere, while in the Mediterranean, this is very common. And during, let's say, the last 10 years, we have developed the so-called infrared reflective materials, materials that they have any color you may wish, but at the same time, let's say, present a very high reflectivity in, let's say, the infrared part. So you may have any color with much lower temperature. And you can see in the graphs that you may have, for example, a pavement which is about 10 to 15 degrees lower surface temperature than a conventional one, even a black one. All these materials have been, let's say, developed and are commercially available, and there are more than 250 large-scale projects all around the world that really this kind of materials are implemented. Then we move to some more sophisticated techniques, color-changing materials for the urban environment, thermochromic materials, materials that when temperature is quite low, maybe, let's say, absorbing black or any color you may wish, but during the summer period when really temperature is high, this material became white and so reflect radiation. And during the next winter, maybe black. These materials are developed. Now they are almost commercially available for cities. And we have, let's say, achieved up to 25 degrees low surface temperature. But during the very last years, and I can say you during the six last years, there is a revolution as it concerns building materials for, let's say, the built environment, or materials for the built environment. And this has to do with the so-called, let's say, photonic materials or daytime radiative coolers. These are materials that present a very high reflectivity to the solar radiation, more than 95-96%, but also can emit in the so-called atmospheric window 8 to 13 micrometers, so they can really reject the excess heat to the space. These materials have been developed and can really achieve a very low temperature. I'd like to show you some of these materials that we have developed here in my lab in Sydney. And during very recent, let's say, measurements last month that we have performed, we have achieved to decrease the peak temperature of the materials. Let's say, and you see some pictures from, let's say, the experiments. As you can see here, under very high solar radiation, about 1,200 watts per square meter, we achieved during the peak daytime period to have about 5 to 6 degrees, sometimes 7 degrees lower temperature than the ambient one, subambient temperature, and during the day up to 60 degrees below the ambient temperature. So these so-called super cool materials really are extremely promising and may really help a lot to decrease the temperature of our cities. You can see some of these materials as developed, the photonic materials, and some results for a recent project with photonic materials we have in Western Sydney. Another stream of important research regarding materials, it has to do with the so-called, let's say, fluorescent materials, especially quantum dots. These are tiny materials that have a very high, let's say, not reflection in reality, but fluorescence. I mean that these materials, when they absorb radiation, they, let's say, re-emit in different wavelengths and fluorescence. So in reality, they do not absorb, so they are not heated. We have developed materials for mitigation materials for, let's say, cities based on quantum dots and photonic materials. And actually, we have achieved to, let's say, achieve almost 11 degrees lower surface temperature by using these materials. This is at this time, at the laboratory test that we plan during the next years really to commercialize this. So where we are, we started, let's say 20 years ago with reflective materials, and we have achieved a decrease of the temperature of cities up to 0.5 degrees. Then we had the so-called, let's say, infrared reflective materials that really helped to decrease the surface temperature of the ambient temperature of our cities up to 1.2, 1.3 degrees. And then materials of advanced technology like thermochromic materials, like, for example, quantum dots, like radiative cooling, and many other things that really are developed. When all these technologies are implemented, and we have more than 450 large-scale mitigation projects all around the world monitored, we achieved to decrease the peak temperature of cities up to 2.53 degrees. With the development of the new technologies that really are now available, will be available during the very next years, we expect to decrease the temperature of our cities up to 4 or 5 degrees. Is this enough? No, it's not enough, because the projected overheating for our cities may be much higher. In this graph, you see the plan for the future conditions in Sydney. The yellow cycle is on where we are today. If we are not really proactive, if we don't apply any mitigation technologies, if we don't care, if we follow a scenario business as usual, we move to the right part. And this means an increase of the temperature of the city by 5 degrees. In Western Sydney, we may have more than 20 days per year above 50 degrees. On the contrary, if we are proactive, if we really apply and implement the developed technologies, not the future one, the existing one, we might move to the left part, which is really a decrease of the temperature by 2 degrees. So there is really hope that can help us really to survive in our cities. But is it mitigation, let's say, enough to respond to climatic change? No. This has to be combined with adaptation techniques, and I mean better buildings. To better understand the combined, let's say, impact of mitigation and adaptation, I'd like to show you some simulations about the energy consumption of heating and cooling load of a commercial building in Sydney, of a residential building in Sydney. In the upper right part, you see the actual energy consumption. The red one is the cooling load, the yellow one is, let's say, the heating load. Once we do nothing, no proactive technologies, nothing, by 2050, the energy consumption will be the second graph, which means that the cooling energy consumption will increase by a factor of 3 without a decrease of the heating demand. On the contrary, if we are using just mitigation technologies, we may move to the third and the fourth graph, where the energy consumption for cooling compared to the 2050 scenario may decrease by 30 or 40%, but still will be about, let's say, 50 or 60% higher than the actual cooling load. But the good news is that once we, let's say, apply mitigation, better cities, and adaptation, better buildings, in, let's say, in our buildings, the cooling load may decrease by 80-90% because we have the technology to do that, and also the same for the cooling load. So there is hope. Once really we applied advanced, technological developments in our cities and for our buildings, yes, we can respond to the climatic change. But it's not just that. We can also save lives. And this is a recent statistic that we have developed that shows how much real data, not simulation, how much the temperature decrease in cities affects heat-related mortality. And you see that, for example, that once we succeed to decrease the peak temperature of our cities up to 1.5 degrees, the heat-related mortality is decreasing by 45%. This is tremendous. And so this has to be seriously taken into account because the real cost of health is tremendous. But also the future, let's say, energy consumption has to be projected in terms of climatic change and in terms of mitigation and adaptation. I'd like to show you an example of a northern city in Australia, an equatorial city, tropical city, Darwin. And the 2050 energy consumption, if nothing happens, will be the upper line, and the energy consumption and the overcooling will be the shaded area. Once we apply business as usual technologies for, let's say, adaptation, better insulation, better ventilation, etc., this may decrease and be this part. Once we apply at the same time advanced adaptation scenarios and adaptation technologies for our building, this may decrease at this specific level. But once we have mitigation to adaptation at the same time in our cities, the energy consumption will be very close to zero. So yes, it is possible despite the overall climatic change, global and local climatic change, to have zero energy settlements, zero energy buildings, for 2050 and respond to the climatic change. In conclusion, we face a very important problem of climatic change in our cities, up to 10 degrees of overheating. And this has a tremendous impact on energy, 200, 300% more energy consumption in some parts. This has a tremendous impact on peak electricity demand, obliging utilities to build additional power plant. And this has a terrible, let's say, impact on mortality and morbidity. There is hope, because actually with the development of advanced mitigation technologies, we are able to decrease the peak temperature of cities up to 2.3 3 degrees, in the future 4 degrees, decrease the energy consumption of buildings up to, let's say, 80, 90%, decrease heat-related mortality by more than 40, 50%, decrease the peak electricity demand by 20, 30%. Is there any condition to do that? Yes, there is a very important condition. The future of the building research has to be done in an holistic and integrated way. What we are doing now is that everyone is following his stream. I'm doing energy, you are doing comfort, he's doing epidemiology, the other is doing, let's say, economics of the building sector. Another one is doing something that has to do with, let's say, sustainability. And we don't communicate. We don't really integrate the results and the findings from the different parts together. So there is a very important condition. In the future, we need to have an holistic approach. We need really to discuss and at the same time integrate our research in a common platform, a platform that will take into account all the different levels that and all the different knowledge and all the different disciplines that affects really the built environment in a more holistic and more integrated way. Thank you very much.